Hey there, this is problem set 7 where we're going to be talking about light and a little bit about quantum theory. If you're curious why we have jumped from talking about atoms and molecules to suddenly talking about light, I think the best explanation is just that light is the best way we have to interact with atoms and molecules and to learn about them. And so in order to use light to learn about atoms, we need to know the properties of light. And so we're going to spend some time working on that. So here's problem set 7. The first question asks to explain a photon in 1 to 3 sentences. A photon is the smallest unit of light. So I guess I could write that. Ooh. So we could call it 1 quanta of light. Quanta just refers to the smallest piece of something. So kind of more technically we could say it's a packet of radiant energy, which is electromagnetic radiation. So when we talk about electromagnetic radiation, that's a whole spectrum, right? So we've got radio waves down at the low energy end, and then we've got like gamma rays at the high energy end, somewhere in the middle, about 400 nanometers to 700 nanometers. This is visible light. And then, of course, higher energy than visible is UV, lower energy is infrared, which we observe as heat. Visible light, we can see color, right? And so, but all of this is really the same thing. It's electromagnetic radiation. It's made up of photons, little white light quanta that have wave-like characteristics. So there we go. That's what a photon is. What does it mean for something to be quantized? I'm going to say only available in discrete quantities. Or like packets, you could say. Yeah. So light, we say, is quantized. We often think of light as being continuous, but what has been discovered is that in reality, electromagnetic radiation, or light, is available in discrete units, and that's where this whole photon idea comes from. That's one discrete unit. Examples of 3 everyday things that are quantized, like stairs. Right? You can only be at that level or that level at that level. You can't be halfway in between. That would be quantized. If we said, like your class rank, I guess, right? You can only be number 1 or number 2 or number 3. Nobody's number 2.5. We could say, apples on a tree. Those are quantized, right? Because you can't have half an apple. So, awesome. All right. Complete the following table. If the wavelength is given, calculate the frequency of a photon and of that wavelength and vice versa. Then calculate the energy of 1,000 photons, the wavelength or frequency of that wavelength or frequency. Label which part of the electromagnetic spectrum each photon is in. Okay, and then if it's in the visible region, state what color. All right, so this is kind of a beefy problem because we're going to get to do the exact same thing over and over and over again. What you need to be aware of in order to solve this problem is just a couple of equations. So first off is that the speed of light is equal to wavelength, which is lambda, times frequency, which is nu. We also need to know that energy equals Planck's constant times frequency. And I could combine these 2 equations into one, which would say that energy equals h, Planck's constant, times the speed of light over wavelength. So this way I can get between, this will switch wavelength and frequency, this will switch frequency and energy, and this will switch energy and wavelength. Okay, so to solve these problems, I'm going to pause real quick. And I'm back, sorry about that. So we can switch between energy, wavelength, and frequency. That's an important principle to understand, that if you're given one of those 3 things, regarding a photon, you have all of those things. And so sometimes you'll see problems where you need a wavelength, but they only give you a frequency. Well, if they've given you a frequency because of this equation, they've also given you a wavelength. So let's just get started. Oh, the other thing to recognize is that the units in these equations. So wavelength is always going to be in units of meters. Frequency is always going to be in units of hertz, which is the same as 1/seconds. And then energy is going to be in units of joules. So I'm going to take those and move them up here so they're out of the way. But that's just important to know. So if they give you units that are not those, you're going to have to change them before you can plug into the equation. All right, so let's start. We're trying to get the frequency from 100 meters. Well, using this first equation, frequency equals c over wavelength equals c over 100, which is going to be 2.998 times 10 to the 6th hertz. Okay, and now we want to find energy. Well, we have frequency, so energy equals Planck's constant times 2.998 times 10 to the 6th. That gives me 1.986 times 10 to the negative 27. Okay, but what is that the energy of? Well, that is the energy of one photon. Why? Well, we use the frequency of one photon when we plug it in right here. That will give us the energy of one photon. As a result, if we want the energy of 1,000 photons, what do we need to do? Just need to multiply that by 1,000. And that will give us 1.986 times 10 to the negative 24. Let's go here. And if we pull up an electromagnetic radiation chart, we can just look at a wavelength of 100 meters and see where that is, and that'll happen to be in radio. Okay, I'm just going to keep going. Hopefully I have enough space to do all of these, and I'm not necessarily going to explain my way through all of them, but I am going to work on them. So now I am working on this guy. I know that wavelength equals c over frequency, which is c over 2.99 times 10 to the 8th. Which gives me a wavelength of 1. 0.00 1 meter. And then E equals h nu equals h times 2.99 times 10 to the 8th. And again, I have to multiply that by 1,000. That gives me 1.98 times 10 to the negative 20, which is also in the radio range. Alright, I'm going to follow the same thing here. Now I'm working on this guy. C over 3 times 10 to the 10. This gives me about 1 times 10 to the negative 3. Oh, 1 times 10 to the negative 2. So that's 0.01 meters, but it's also 1 centimeter. And then energy equals h times 3 times 10 to the 10. That gives me a value of 1.98 times 10 to the negative 20. Which is in the microwave region. Alright, so we went from 100 meters to 1 meter to 1 centimeter. Now we're going 1 millimeter, but remember we need to have the correct units. So it's going to end up being frequency equals c over 10 to the negative 3 meters. That's going to give me a frequency of 3.0 times 10 to the 11. And when I do E equals h nu, oh, I forgot to multiply by 1,000 times 1,000. That gives me 1.98 times 10 to the negative 19. And that is in the IR range. Okay, here we've got a frequency. We know that wavelength equals c over 3 times 10 to the 14, which is going to give me about 1 times 10 to the negative 6 meters, which is 1 micrometer. And then when I plug that E equals h nu times 1,000, I'm going to get 1.98 times 10 to negative 16, and that happens to be right around UV X-ray range. Okay, now that takes me to 750 nanometers. 750 nanometers. Frequency is going to be c over wavelength equals c over 750 times 10 to the negative 9. And that gives me about 4 times 10 to the 14. Which, when I change into energy, give me about 2.65 times 10 to the negative 16, which is about visible, and that's red. So again, that would just be energy equals h nu equals h times 4 times 10 to the 14, and then I'm going to multiply that by 1,000. Okay, so hopefully you are getting the hang of this. I'm just going to fill in the rest of the chart, which you could practice. And these electromagnetic spectrum ranges are pretty fluffy, so I wouldn't pay too much attention to them. UV, wow, V, 100 nanometers gives me 3 times 10 to the 15, 0.98 times 10 to the negative 15, which is also in UV, and then 3 times 10 to the 17, 0.98 times 10 to the negative 13, which is around X-ray. Okay, hopefully that's enough practice switching between wavelength, frequency, and energy. You're going to end up doing a lot of that in the context of other problems, so it's important to have that skill. All right, number 3, a typical microwave oven operates at 2.45 gigahertz. Calculate the wavelength of electromagnetic radiation. Perfect example. We've got a frequency. I know it's a frequency because it's hertz, and we need to get it into a wavelength. So first off, 2.45 gigahertz is the same as 2.45 times 10 to the 9 hertz. So then I can say my wavelength is going to be c over frequency equals c over 2.45 times 10 to the 9. And that gave me about 12, or I should say 0.122 meters, which is 12.2 centimeters. So that's the wavelength of this microwave. How many wavelengths does it take for the wave to travel the length of a 30.5 centimeter wide microwave and back? So let's say we've got this microwave we're just sending this wave across and sending it back. So what's the total distance it's going to cover? Is going to be 30.5 times 2, which is going to be 61 centimeters. And I know the wavelength is 12.2, so I do 61 centimeters divided by 12.2 centimeters. Gives me 5 wavelengths. And that's to go all the way down and all the way back. So how many nodes occur? I'm going to draw a picture here. So if I've got my microwave, I've got 2.5 wavelengths each way. Wow, it's not going to fit. I'm going to draw the wave first. 1, 2.5. So here's my microwave oven with a microwave in it. Okay, but now it's going to come back on itself. So you can see there we have going forward 1 wavelength, 2 wavelengths, and then when you come back you hit 3 wavelengths, 4 wavelengths, 5 wavelengths. How many nodes occur? So we would say that there's a node right here, node right here, node right here, node right here. So I would say 4 nodes. Okay. Do the nodes for standing waves travel in the forward or reverse direction? Oh, do the nodes for waves traveling in the forward and reverse directions line up? Does it form a standing wave? It does, because we saw it because we get exactly 2.5 wavelengths one way and exactly 2.5 the other. So yes, and that makes it a standing wave. And the result of that is the wave isn't moving forward or back necessarily. It looks like it's just flopping up and down, which is why we get these nodes where there's no movement. And what happens to food placed at those nodes? Well, how much energy is there in the wave right here? Nothing. And so food there isn't cooked because there's no energy in those nodes. And then why do we spin food in the microwave? To I would say to limit the effects of nodes, right? Because you want your food to cook everywhere, and so you want to make sure those nodes aren't hitting the same part of the food every time, all the time. So we spin it. There you go. All right, the 4 centimeter band is a portion of the radio spectrum that is allocated to amateur radio and amateur satellite enthusiasts. What is the frequency of electromagnetic radiation with a wavelength of 3 centimeters? How does this compare to the 60 Hz frequency of the oscillations of alternating current, AC, and electrical power grids? So, 3 centimeter band, what is the frequency? Well, we know frequency equals C over wavelength. C over 3 centimeters is 0.03 meters. That gives me a frequency of about 1.0 times 10 to the 9. Is that right? 2, 3, 4, 5, 6, 7, 8, 9. Okay. Why did I get 9? Maybe did I got 10? Oh, it is 10. There we go. 1.0 times 10 to the 10. Thought that seemed weird. And so there is our frequency in hertz. Now the question is, how does that compare? Well, there's different ways you can compare this. Obviously, if this is 60 and this is the power of like 6 times 10 to the 1. This is 1 times 10 to the 10. So this is like 9 orders of magnitude bigger. So a lot higher frequency, a lot higher energy waves compared to our electrical power grid. Okay. Prolonged exposure to ultraviolet radiation in tanning booths significantly increases the risk of skin cancer. What is the energy of a photon of UV light with a wavelength of 3 times 10 to the negative 7 meters? All right, so we want the energy. They're given a wavelength. So jumping up here to these equations, we've got this guy that relates energy to wavelength, and so I'm just going to use that one. So E equals hc over lambda, hc over, and in case, let me plug in. So h is 6.626 times 10 to the negative 34. C is 2.998 times 10 to the 8. And then lambda is 3 times 10 to the negative 7 in this case. And when I plug those in, I get about 6.62 times 10 to the negative 19 joules. That's how much energy is in a photon with that wavelength. When dentists take X-rays, the patient is given a protective shield from excess radiation. How much more energy is there per photon of a dental X-ray than a UV than from UV radiation? These should be lambdas. Just doesn't convert right on my computer. All right, so we're trying to find the difference in energy between this X-ray and this ultraviolet radiation. So energy of the X-ray is going to be hc over 71.2 times 10 to the negative 12. That's a picometer. And that's going to equal 2.79 times 10 to the negative 15 joules in your X-ray, and then the UV, hc over 250 nanometers, so that's times 10 to the negative 9. That gives me 7.95 times 10 to the negative 19 joules. And I want to find the difference, how much more energy in the X-ray. So 2.79 times 10 to the negative 15 minus 7.95 times 10 to the negative 19. And what we'll see when we do that math is we get about 2.79 times 10 to the negative 15. And the reason is, this is to the negative 19, so it's like the decimal is moved over 4 more times than this first number, and the result of that is this second number is, relatively insignificant compared to the first number. And so that's why the difference is really just that first value. We could also relate these as a proportion. We could say 2.79 times 10 to the negative 15 divided by 7.95 times 10 to the negative 19. If we do that, we find out that this X-rays is 3,509 times higher energy. So that's a second way to relate it, since that first one doesn't really tell us all that much. All right, the problem keeps going. It says medical X-rays are often produced by slamming fast-moving electrons into pieces of tungsten metal and can have wavelengths as small as 20.9 picometers. How much energy is in one of these X-ray photons? Well, we know energy is hc over wavelength. In this case, the wavelength is 20.9 times 10 to the negative 12. And when we do that, we get 9.50 times 10 to the negative 15. Hopefully by now you've noticed I'm not too concerned about keeping track of my significant figures in these problems. I kind of do the best I can when I remember, but for the most part I'm more worried about the principles taught on these particular problem sets than the semantics of significant figures and things. All right, it takes about 3.9 electron volts, that's what that EV is, electron volts, to break apart or severely damage DNA. And they give you the conversion factor to joules. Can UV light, dental x-rays, or medical x-rays damage your DNA? All right, well, we have the energy of UV light, dental x-rays, and medical x-rays. I think these are medical x-rays. These are dental x-rays. We have the energy of all those in joules. So if we can just figure out the energy required to break DNA in joules, we can compare them all. So we could say I know 3.9 electron volts breaks DNA, and they tell me that 1 electron volt is 1.602 times 10 to the negative 22 kilojoules, but I want joules. Add this in the last step, 1 kilojoule is 1,000 joules. So 3.9. So I do that, and I get an energy of 6.25 times 10 to the negative 19 joules are required to break DNA. Are any of these above that? Well, 6.25 times 10 to the negative 19. Here we go. 6.22 times 10 to the negative 19. So that's nearly there. Wait, no, that's higher. So UV light is higher. Energy of X-rays is higher. And energy of medical X-rays is higher. So all of these could damage your DNA. Because they're all higher than that minimum amount. All right, moving forward, what is blackbody radiation? Blackbody radiation happens when you have an opaque, well, I guess I could say a black body is like an opaque, non-reflective object. So like the coils on a coiled stovetop, those are black bodies. They don't reflect any light, which is why they come off black. But if you were to pump enough energy into those, they will start emitting light. That light they emit is blackbody radiation. So blackbody radiation would be opaque, non-reflective objects emitting light at high temperatures. This is also how classic incandescent light bulbs work. You've got a filament in there that's a black body. You can pump enough electricity through it that it heats up, and when it gets really hot, it starts emitting light. So they give us this example of this lava flow. It says that the temperature can be estimated by looking at the color, because this lava is a black body. Estimate the temperature of the hottest part of the lava. So I'm just kind of, I don't know, this like really white part there looks like the hottest to me. And it looks like it falls somewhere between these two, 1080 and 1205. So I'm just going to say about 1200. And this is degrees Celsius. And obviously that's kind of up to judgment, but... Alright, blackbody radiation can also be used to study stars. If star A radiates light with a maximum intensity of this many nanometers, this might make more sense if we said wavelength instead of intensity. Star B with a maximum wavelength or intensity of 480 nanometers, which star appears more blue? Knowing that the visible range is between 400 and 750. So the best way to think about this is I know that I have 400 nanometers, 750 nanometers, and I know that 400 is going to be higher energy, so I just think red, orange, yellow, green, blue, indigo, violet, Roy G. Viv, just kind of backwards there. So which is going to look more blue? We've got a 650, which is going to end up around here, and then we've got a 480, which is probably going to end up around here. So I would imagine that the 480 star B is going to be more blue. And the 650 is going to be more orangish. Orange, yellow, reddish. All right, which radiation has the higher frequency? The red light on a barcode reader at a grocery store, or the green light on a battery charger for a laptop computer? Well, we could look at our scale here. Red falls here, green falls here. Which of those is higher energy? Well, red is higher wavelength. But if you remember, E equals hc over lambda. So a higher wavelength, because it's on the bottom, will end up making the energy lower. So higher wavelength, lower energy. So the green light is going to be higher energy and therefore higher frequency, because if you remember, E equals h nu. So if energy goes up, frequency goes up. So energy and frequency are proportional. They go up and down together. Wavelength and energy are inversely proportional. They go up and down opposite of each other. All right, the work function of a material is the minimum energy required to emit an electron from the material. The work function of silver is 7.59 times 10 negative 19 joules. So maybe let's take a minute and talk about work function. So work function goes back to this principle of the photoelectric effect, which is if you have a photon and you throw that photon at a piece of metal, it could potentially kick off an electron. So the thing is, there's a threshold energy, a minimum energy required for each metal to kick off the electron. We call that the work function. And so I could calculate the energy of this photon as h nu. And if I know the work function of the metal, which we usually give this little symbol, as long as the energy of the photon, h nu, is greater than the work function, then we have enough energy to kick off an electron. Okay. If the h nu is a lot bigger than the work function, what's going to happen is all that extra energy is going to be absorbed by the electron, and the electron is going to be kicked off faster. So we could say the energy of the photon is going to be equal to the work function, and if the energy of the photon's bigger, the rest of it is going to go into the kinetic energy of the electron. So if I'm in Australia and I'm wearing silver earrings, the sun comes out irradiating me with light, has a wavelength of 185 nanometers. So this photon has a wavelength of 185 nanometers. Will electrons be emitted? So when are electrons emitted? They're emitted when the energy from the photon is greater than the work function, which is the work function is the minimum energy, right? So I'm trying to figure out if the energy of the photon is greater than that work function for silver. Well, I have the wavelength, and I know that E equals hc over lambda. Hc over 185 times 10 to the negative 9. And when I do that, I get 1.07 times 10 negative 18. That's the energy of my photon. And the work function is 7.59 times 10 negative 19, which means this is bigger, which means the answer is yes. We're going to kick off electrons because our photon has more energy than the work function, and the work function is the minimum energy to kick off an electron. If radiation hits me that has more energy than required to emit an electron for my silver earrings, which we just established is yes, what happens to the additional energy? Well, what doesn't happen to it is it does not go to kicking off more electrons. Okay, just like if you were to swing your foot at a soccer ball, if the more energy you put into your foot does not kick more soccer balls, it kicks the one soccer ball harder. So we would say that additional energy becomes the kinetic energy of the electron. All right, so now I think we have a similar problem here for 10. 10A, there is no 10B, okay? Steel and iron are often galvanized or coated with a thin layer of zinc metal to prevent corrosion. Iron rusts, but zinc does not. What is the longest wavelength of light in nanometers that can eject electrons from zinc metal? Assume the electron's kinetic energy is very close to 0. The work function of zinc is that, and then they give you conversion factor. All right, one thing to recognize is whenever you see something like this longest wavelength, remember E equals hc over lambda. So what is longest wavelength? Lowest energy. So what is the lowest energy of light that can eject electrons from zinc metal? Well, we just said the definition of work function is the lowest energy required to kick off an electron. So what we're trying to find really is the work function. Or do they give us the work function? Oh, they give us the work function. And so that is the lowest energy to kick it off. So we're trying to figure out what wavelength for a photon has that much energy. Okay, so again, we've got our metal, got a photon, bam, we want to kick off an electron. We know the minimum energy to kick off an electron. So if a photon had that minimum energy, the lowest possible energy, exactly the work function, that photon would have the longest possible wavelength to kick off an electron, because anything longer would be too low of energy. So really all I'm doing here, I got to get my zinc energy into joules. So in joules, my zinc's work function is 6.9 times 10 to the -19. Okay, and now I want to find what wavelength of light has that much energy. So I say wavelength equals hc over energy, which is 6.9 times 10 to the -19. And I get about 2.88 times 10 to the -7 meters, which if you want, you can convert it to 288 nanometers. So what this means is if your photon had 288 nanometers of wavelength, it would have the lowest possible energy to kick off an electron. If we had a longer wavelength, what happens if I increase the wavelength? The energy drops. And so any wavelength longer than that will not emit an electron anymore. And so this is the longest wavelength of light that can eject electrons from zinc metal. So there's a couple of examples of work function type problems, as well as just an introduction to light in problem set 7.